Okay, here we are. This is on a Jolida amplifier, SJ202, and this is part 5 we're starting here. What we had been doing before is we were running a dummy load over here. We were running light bulbs as our load. So the next logical thing to do was to take the wires that we were running to the dummy load, the light bulbs, and to bring it back to the amplifier using our bridge circuit that's on the breadboard and our capacitors that are set up over here. So this is the Jolida circuit on the breadboard using Schottky diodes and the capacitors in series with a voltage divider. And right now we have the amplifier, and we're actually we have an audio signal coming into it, 350 millivolts, and we've got a dummy load hooked up to the amplifier, 8 ohm taps going to 8 ohm resistors, precision resistors. Everything is turned on, and you can see the transformer is producing 300 volts, and with the volume turned all the way off, we're drawing 331 millivolts. I'm sorry, milliamps of current. So we're at 300 volts, 300 milliamps of current. Let me double check the volume. Volume's all the way down. On the DC side, we're at 379 volts DC, and we've got 180 milliamps of current draw, almost 200 milliamps of current draw. This is the volumes turned all the way off on the amplifier. Okay, the signal on the oscilloscope, we can see we've got 790 volts peak to peak with a 5 volt ripple. Okay, we're back. The volume on the amplifier is turned max all the way up. We've got a 740 volt peak to peak from the power transformer to the amplifier with 11 volt ripple. Once again, we got 350 millivolts coming into the amp, and this is what the power transformer looks like. Channel A, the red coming out, and then the channel B, the blue, is a ripple off the DC side of the bridge rectifier. Alright, this is RMS 287.88 volts RMS, and at 711 milliamps of current. That's the AC side of the bridge, or the output from the power transformer. This is what the volume at max. On the DC side, we got 358 volts DC at 426. So this is the current draw DC, 426, and what the voltage, the B plus voltage, would look like at max volume. Okay, there's the output wattage from the amplifier. With the 350 millivolt signal going in, we got 39 watts out. According to Jolida's information, at 300 millivolt input signal, I should be able to get 40 watts out, which we're pretty close. As for distortion on this thing right now, I've got 5.5, 5.6 THD. That's total harmonic distortion plus noise. And the signal, you can see this is the output signal from the amplifier. You can see it's clipped, and then channel B on that is I believe that's a representation of signal and noise. The spectrum, each vertical line is 1 kilohertz. So you can see the signal is at 1 kilohertz. That's our primary signal. That 350 millivolts is at 1 kilohertz. So you can see that that's the first of the spectrum, and then every odd you can see it's higher than the evens with regard to spectrum. Center frequency on this is 5,000 kilohertz. So the 5 and the 3 look pretty much pretty close to the same, 5 being a little bit lower. And so this is a spectrum max volume. Now this thing is rated for 30 watts at 1%, so we're going to turn it down to 30 watts and see what the signal looks like. Okay, we took the output of the amplifier and decreased it to 30 watts output. This is with the 1 volt input signal into the amp at 1 kilohertz. So we got 740 volt peak to peak with a 10 volt ripple. We're drawing 640 volts, 640 milliamps of current at 288 volts off of the power transformer. That's the AC side. That's the output of the power transformer. Once again, rated at 300 milliamps, 300 volts. But this is at the rated output of the amplifier. Over here on the DC side, we're 367 milliamps at 358 volts, B plus for the amplifier. There's the bridge again. And again, this is at 1 volt into the amp and 30 watts output from the amp. So we'll go take a look at those numbers. Okay, there's the display showing the 30 watts, 30.6 watts output from the amplifier. Our total harmonic distortion plus noise is 0.5. Our single looks like a normal sine wave, and then that lower is again the distortion characteristic. The spectrum at the 30 watts, once again, looks a lot better. This is what the 1 volt input. Oh, that's what these displays look like. I'm gonna put another IR shot in right here so we can see what these diodes look like. Looks like the diodes are getting kind of warm. So let's get the IR shot so you can see what that looks like. Okay, one of the things that caught my attention when we were running some of the previous tests was that the current draw off of the power transformer, I think, was like 180 milliamps at idle with the volume turned all the way off. And I thought, well, if the power transformer is only supposed to put out 300 milliamps at 300 volts, and with the volume all the way down I'm drawing 180, that's like half of its output. So that also made me question, why is that so high? So what I thought we would do is isolate the tubes on this thing. Basically pull one tube out at a time and see what type of current draw and how it affects it. So once again, here's the AC side. We've got 305 volts and we're pulling 300 milliamps right now. I don't know why that's so high, but it is. Supposedly that's the output of the transformer, according to the data plate on it. On the DC side, our load is 184 milliamps, and our B plus is 389. Once again, we're on the Schottky diodes on the breadboard. You got the amp up on its side now, so we can remove tubes one at a time. We have the oscilloscope hooked up. It's showing 880 volt peak to peak with a 6 volt ripple. The input to the amplifier is basically grounded. One lead is tied to the other on both channels, and the volume is turned all the way down. The output runs to the dummy 8 ohm loads. Once again, this is our idle current draw on the power transformer. This is connected to the output of the power transformer, the input of the bridge, and it's supposed to be 300 milliamps. 300 volts is what the transformer is rated for, and right now, with no signal going into the amp, and the volume turned all the way down, we're basically drawing full load of that transformer. Kind of makes me wonder why. Alright, we're going to unplug tubes one at a time, and we're going to see what happens. Okay, we removed V1. It's the preamp tube. It's a 12AX7, and these are the numbers. We're drawing 300 and almost 50 milliamps, and our voltage on the transformer is 305. So that's the transformer side of the bridge, 350 milliamps at 305 volts. Once again, it's 300. On the DC side of the bridge, we got 190 milliamps at 387 volts on a B plus rail. That's what V1, a 12AX7, removed from the amplifier. The oscilloscope, 790 volt peak to peak with a 6 volt ripple. Alright, I wanted to show you the schematic. This is the amplifier board on the schematic, and on the left you can see V1, the 12AX7, and then that goes into a phase and splitter inverter, and that would be V2. So V2 will be the next one that we pull out from the phase inverter or splitter. We feed right over to V3 and V4, which are our output tubes. And then for the I believe this is the left channel. For the right channel, they use, I think it's 5 and 6 are the 5 being the 12AX7, 6 being the 12AT7, and then 7 and 8 are our output tubes. So we're going to pull these one at a time, starting with the preamp and the phase inverter first, and see if this has any effect. And basically what we're doing is we're from the bridge, we come out, we go into the there's the two caps that are in series, and then the voltage divider to ensure each cap. There's the B plus rail before R22, and that comes on up and comes on over to an audio transformer, the output transformer. Then there's the voltage divider R22, and that feeds up to the phase inverter, and after R22 there's R21, and R21 comes on over to the preamp tube. So basically what we're doing by unplugging these tubes is eliminating any current draw on these points. So we want to see if we get some kind of nosedive on that current from the transformer. Once again, the transformer is there, and the transformer output is where we've got the meters connected, a current meter feeding right into the bridge. So we want to see if there's any kind of nosedive on that thing when we unplug one tube, and specifically to see if there's some kind of large decrease in current, which would tell us that something is going on in that part of the circuit. So that's what we're trying to accomplish here. Okay, V6 is out now. That's 12AT7. That's the phase inverter on the right channel. Once again, we're kind of hoping to see some kind of major drop on this current draw on this transformer. Hasn't happened so far with the small tubes. Right now with V6 out to 12AT7, we've got 344 to 350 milliamps the current draw, and our transformer output in volts is 304 volts RMS. That feeds into the bridge. Coming out of the bridge, we've got 186, 187 milliamps of current, and our B plus rail voltage is 386. The oscilloscope, 790 volt, 800 volt peak to peak with a 5 to 6 volt ripple. Alright, we'll move on to the larger tubes and see what happens there. Okay, this time we removed two of the EL34 output tubes, V4 and V3. Should say V3 and V4. We pulled both of them because I wasn't sure that I could just pull one. So I thought we'd get both of them out. I didn't know if I'd create some kind of imbalance on the audio output transformer, so I pulled both just to be safe. And I figured we'd look at the numbers. So here we go. Transformers putting out 235 milliamps at 308, 307 volts AC. It's going into the bridge. Coming out of the bridge, we've got 121, 122 milliamps, and we've got 395 B plus voltage. That's with both, for the left channel, both output tubes pulled out. On the oscilloscope, we're looking at 810 volts peak to peak with a 4 volt ripple. Still has that clipping going on, but those are the numbers there. Also wanted to just touch base again on the way we're actually measuring it. This is where the meters are placed. Once again, the pink is the oscilloscope A channel. That's the peak to peak measurement on the oscilloscope. The B channel is the blue. I don't know if I mentioned, but A channel is pink. B channel on the oscilloscope is blue. The green is the current meter on the AC side. The bright yellow is the voltmeter on the AC side. In the center there we show the two capacitors with the voltage divider. Those are 470 microfarad capacitors, 450 volt, and the dividers I believe are 62 or 68,000 ohms each. Orange is the voltmeter on the DC, and the yellow, once again the darker yellow, is an amp meter on the DC side. We replaced the light bulbs with the Jolida amplifier, so this kind of shows you what's going on there. That's where we're taking the measurements from, and that's what we have. Okay, we'll pull the other two output tubes and we'll see if there's any change, but as this looks, I don't see anything groundbreaking happening here. Okay, we've removed V7 and V8. These are the output tubes for the right channel. They're EL34s. Here's the power transformer. We're putting out 311 volts and drawing 210 milliamps of current. So there's a slight decrease there. On the DC side of the bridge, we've got 105 milliamps of current draw and 397 volts on the B+ rail. So there's a slight improvement here with those two output tubes removed. Not enough to make me feel great, but slight improvement. On the scope, we're 810 volts peak to peak with a 3 to 4 volt ripple. No, it's pretty steady at a 3 volt ripple. So that's what the scope looks like. Maybe we'll look a little bit deeper here and see what we can find out. Okay, we pulled V3 and V4 again, the EL34 output tubes. Last time we pulled them, we're pretty much pulling 235 milliamps of current on the transformer. But this time, what we did is we just transferred the tubes instead of keeping V7 and V8 in there. We transferred V3 and V4 over to V7 and V8. This way we would know that we're just in case there's any difference in the tubes. And what we find is that there is a slight difference in the tubes, and when we transfer the tubes over to V7 and V8, we see the same, instead of the 235, we see the lower current draw, the 205. So what this does is it verifies that the circuit board, we just lost that one. Hang on for a second. This verifies that the circuit board is good, and that the variation that we saw is in the output tubes. So once again, there's the AC side, 310 volt from the transformer, 204 milliamps of current that's putting out. This is less two output tubes, V3 and V4. The left channel output tubes are pulled out of the amplifier. On the DC side, 395 on the volts and 103, 102 on the milliamps. And the scope, 810 peak to peak on the output of the transformer with a 3 volt ripple. Alright, so what all of this points to is the circuit board performs the same left and right when we pull each individual tube or sets of tubes. So it doesn't appear that the fault is in the circuit board. So there you have it. We got another meter timed out. Okay, we brought that meter back. So what I'm thinking is that we might, instead of right now we've got everything wired up on these Schottky diodes, we might move everything back over to these $23 1500 volt reverse voltage diodes, and see if we get the same performance instead of using these Schottkys. That's probably the middle ground between the 50-cent diode and the $8 diode, is go with the $23. Put those back in the board, but I think I want to run a breadboard with it. Maybe get an IR shot of the amplifier when it's running like this to see if we could see anything heating up on it. I tried getting an IR shot, but there's no way to get it on camera. Maybe I could take an individual picture and get that IR shot in here so you can see what's going on there. Okay, to be continued.